From our free body diagram, then we have, we're going to do momentum, our principles, and so momentum is vectorial solution, and we know that for each vectorial direction, so we'll pick we have the r direction, the z direction. Start with the r direction. We know we drew our positive way this way. We know that the change of the momentum of what I chose my system, which is a student, with respect to time, is the net forces. So it's the sum of all the forces acting on that student. Change of momentum, and the momentum is mass times the velocity. We'll assume the mass of the student is constant. So change of velocity versus time. Change of velocity is acceleration. So we'll have mass times acceleration, and we know that in the r direction, these are the formulas then for the radial acceleration, and it's negative, which is very important to remember. So it's towards the center. So there's the terms for my acceleration, or my change in my velocity with respect to time. And we know, so that term is the net forces in the r direction. And in the z direction, we do the same thing. So we have momentum. I could do the same sort of thing here, but we're saying that the student's rotating in this fixed plane going around. He has no velocity component in the z direction. Doesn't change, so he has no change in velocity also with respect to time. So we know all this is going to turn out to be zero. So zero is going to be the net forces in the z direction. So net force is z direction 0, which leaves the only net force we have is in the r direction. We don't need to solve exactly what the forces are. We don't need to know which each one of these forces are to say what the net force is. We know it's the change in momentum with respect to time, which is this. So just using that, we know we'll be able to find what the net force is without solving it for individual forces. So sum of the forces in the r direction, which is the net force, is going to be this term. So it's substituting in the mass. From previous, we had the omega term. The radius of the Earth, the radius at Purdue is radius of Earth times the cosine of the latitude, and then typically, so I'll draw my double lines there. So this all here, then I'll double lines, and I'm gonna do my unit conversion to convert kilometers to meters. And I know that a Newton is a kilogram meter per second squared. Everything's crossed out, it ends just with newtons, and turns out to be minus 1.795 newtons. And the negative sign says that I chose my positive r direction this way, negative means this way, so the net forces is inward. The vectorial direction of all the forces, the sum of all the forces acting on the student, which is the net force, acts directly towards the central axis on the Earth, and that's the magnitude. Now, next part of the problem, it asks for the magnitude and direction of all the forces acting on the student. So we'll just kind of rewrite this again. This time I'm going to worry about rather than net forces, all the forces. So I can just jump to, because of this r direction, I know this is this term right here, rewritten. And now I'm just going to look at my free body diagram and look at every force I had on there, and then look at the vectorial component in the r direction. So I have my gravitational attraction force to the center of the Earth, and vectorially it's going to be this, and it's in the minus r direction, and the plus r direction is this component, the normal force to the cosine of theta. On this drawing, I arbitrarily drew the frictional force as perpendicular to the normal force, and I drew it down. If I'm thinking about it some more, I might have chosen it up, but I chose down, and so we'll stay with that. And so if this magnitude turns out to be negative, means that actually the force is that direction. And for most problems, you probably want to use your intuition and draw this force in the way you think it really is. So if a box or something is sliding this way, you probably think the frictional force is that way, and should draw it that way, because that just makes, when you solve it all up and the frictional force turns out to be positive, then it means the direction you thought was correct. I mean, if you're wrong and you think, well, frictional force is that way, when the box is sliding this way, which I mean, it's going to turn out that frictional force is negative, which just means that that in that direction it's negative, so that it'd be positive in this direction. So ultimately, whether you choose to draw which one way or the other, is preferable to do this way, because I think just ending up with a positive just confirms your choice. And we'll find out later why it might have been better to choose it this way, but I drew it this way, and it kind of going to prove a point here. So in the r direction, we know, so this is a positive. If I break that into vectors, that's a positive. So positive friction force, and this time it's the sine of theta. And then I have my buoyancy force, and so buoyancy force is in the positive direction, cosine theta. So that's all the forces I drew on my few-bit diagram in the r direction. Now looking in the z direction, we said that this term is 0. It doesn't accelerate up and down or have a change in velocity or change in mass in the z direction. So that was 0. And now again we'll do the gravitational force has a minus z component. The normal force has a positive z component. The frictional force has a minus frictional force cosine theta, and the buoyancy force has a positive term. So all the forces I described, so now I have these two relationships that can help me solve for the magnitudes of all the forces. Buoyancy is a somewhat confusing issue, so I'm going to take a split here and to talk about buoyancy, and I'm going to talk about a condition which is more commonly associated with buoyancy, is something floating in water. So we have this bowl floating in water, and I'm assuming everything's going to be static. We're not going to have anything moving. So what forces are acting on this bowl? It says bowl has made up some material, kind of this outline right here, and we have a gravitational force from that bowl material. So that's the mass of the bowl times g. We know that another way. So density is mass over volume. So mass is density times the volume of this bowl material. So another way to write this term would have been the density of that bowl material times the physical volume of that bowl material times g. So that's one force. Another force that's acting is, with this water level, some of this bowl material, essentially the outer outline of this bowl, all the way, considering all that volume of stuff that would have been, that if the bowl was gone, would suddenly be filled with water. So that all that volume, all that stuff inside here, so all this volume of stuff, okay, that's the water displaced. So there's a buoyancy force for that displaced volume, and that's shown by this red outline and all the stuff that's moved. And that buoyancy force which is from the water acting on the bowl is the density of the water times the volume of all this water displaced times g, and that's a positive outward from the center of the earth. Okay, then to be totally accurate, there's also this volume, which is just the bowl material sticking up into the air. Well, that's displacing air. So there's a buoyancy force on the bowl from the air. So the buoyancy force on the bowl from the air is just the density of the air times the volume of this bowl material sticking up in the air times g. So that's because that's buoyancy. And the force we're going to consider here is kind of like this force right here. Now, typically you ignore it because the density of the air is maybe about, so we're assuming it's like, about a little less than 1 out of 800 parts to the density of water. Density of water is typically 1,000 grams per meter squared. So the ratio of 1,000 to 1.1225 is 800 and something. So typically, this is a very small impact, but for this problem I said don't ignore it. Looking at these two equations, we see we have terms, we know m, we know omega, we know rp, we know these terms. We don't know Fn right now, we don't know Ff, we have F buoyancy. So two equations, F buoyancy, we talked about before, F buoyancy is just G times the density of the air times the volume of air displaced. Well, we know the volume of air displaced is the volume of the student in this case, and the mass of student is the density times the volume of student, so I can replace this with the mass of student and find the buoyancy force is G mass of students in the ratio of the density of air and density of students. Now that's a known term. So in here I have two equations. The only unknowns I have of Fn and Ff. Two equations, two unknowns, I can solve for it. There's many ways to do this algebraically. Here's the way I chose to do it, by substitution. So I'm going to take this equation 2, we'll solve for f of f. So bring it over there, these terms. Then more algebra, bring the cosine over here. Now I have f of f in there. And I can substitute this f of f term into here. So for here's now equation 1. And I'm going to just replace f of f with this term. And then buoyancy with this term right here. So now I have one equation. The only unknown is Fn, so I just need to solve for Fn. I'm not going to do the algebra here, but just rearranging things, and remember sine squared plus cosine squared equals 1. That'll help you to simplify it down to this term. So that's simple algebra. There's Fn. Mass times this quantity of minus omega squared rp cosine theta plus G times the quantity 1 minus the density of air or density of water. So substituting in here all the values that I know, I solve. Here's my Fn. So 600, and I'm going to carry lots of decimal points because we made these assumptions about very small forces. So traditionally you wouldn't have this many decimal places, but I'm just carrying that to help doing that here. Now I have Fn, and I know I have f of f, and 2b, or 2b here is a function of this term and then Fn in there. So I can just put this value into here, solve for f of f, and I end up saying it's a minus 1.164 newtons. So what does that minus mean? That minus means that in reality the direction that it's in that vector orientation, but it's going to be pointing upwards rather than downwards, and that kind of makes sense. You kind of think as the Earth spinning, things want to go towards the equator. Has a central bulge to it. The actual radius of the Earth is smaller at the poles than it is at the equator, because things want to slide down, and because things want to slide down. So this mass wants to go this velocity. There's going to be a frictional force on the surface that's going to resist it. So it's going to be in this minus direction of that. So this minus sign is very important. It helps us to feel good about that. And this is a plus sign, makes us feel good about f of n being the direction we expect it to be. Now Fg is just for gravitational force. I mean that's just our and here that's just that's mg, right? So we can say 686 newtons was just the 9.8 times the 70. So you can kind of see the ratio between these two. So in the traditional view of the world, where nothing's moving, that the coordinate system's on the Earth, you would say Fn is this. Now considering the Earth's rotating at this speed, we know that Fn really is this as opposed to this. F buoyancy, we know all these terms. We could have solved for that really easy. So here's my buoyancy term. Okay, and I said it was shown this vector direction, so there's what it is. So, what kind of approximations are there? So if we kind of look at, so what assumption do I normally make by assuming that the density of air is much less than the density of water or the student? Well, this gravitational force over the buoyancy force is a ratio of 816. So it's just 1 out of 816 is so much less than 0.1% error by in my normal assumption. For any problem involving friction, we should always check the ratio of the sliding frictional force between the two bodies and the normal forces. The ratio of these two magnitudes is this value, and we need to always compare that against the coefficient of static friction. So if the coefficient of static friction is greater than that value, then indeed the person won't slide on the surface and it'll be static and this solution is correct. However, if the coefficient of static friction is less than this very, very small value, then these equations are no longer correct in the form as they're shown, because these are no longer independent, and the frictional force is the coefficient of kinetic friction, or the sliding friction, times the normal force. So in this equation, both of these equations no longer would be independent, but the frictional force would be substituted for this, and so I could solve just equation number 1, and we'd come up with a new normal force. It would no longer be that value. In this equation right here, we'd have a new value for frictional force, and we'd also we no longer have this assumption that there is no z zero velocity in the z up and down z direction, because this person would be sliding on the surface. So if this were true, we just resolve the problem. So that's a check one I should always do to compare that to the coefficient of static friction.